Okay, let's resume our discussion about indexes, starting with the B plus tree index. This is something that you're going to implement for project 2. So pay attention and make sure you understand all the algorithms that are going to be discussed for this index structure. So we talked about different, let's say, APIs. So let's go over here. Overview of indexes. So this is two main types of indexes, I said, right? So the search key is the attribute on which the file is indexed, and then it's also called the index key. So you can use them interchangeably. And the B plus tree index is good for both range and equality search. The primary consideration for designing these indexes is efficiency. Efficiency of search, insertion, and deletion operations. And that means you want to reduce the amount of disk I/O you need to do, because these data structures are secondary storage aware. They can be larger than main memory. They can fit some of these pages on disk, but you want to make sure that you reduce the amount of page reads from disk and page writes and so on. And for the B plus tree index, range search, insertion, and deletion all start with the equality search. Okay, so then what we need to understand is how does the equality search work, and that's what we're going to talk about as the first algorithm. So you can just jog in your memory about all these things. And so let's get to the search algorithm. Here's a toy example of a B plus tree index, what it would look like, and this is an abstract representation. We will get into the details of exactly what this page looks like. So each of these nodes is a page, and in each page you have a bunch of entries. These numbers are basically your key values. Okay, so those are your search key values that the index contains, and then these slots over here are your page IDs. They are basically pointers. You can think of them as pointers that point to children pages. And so in this particular root node, you have 4 key values, 4 plus 1 pointers, or 4 plus 1 page IDs. And this index is on some integer. Let's say this is the movie ID. Now, this node on top is the root node. Just like with any tree data structure, you have a root node. And what the semantics of this means is if an index key comes in, you need to compare it with these key values over here. Okay, so some metadata about this tree. Its height is set to be 1. So if the tree has only the root, its height is set to be 0. The order is a parameter that determines how many keys exist inside each node. And the order here is 2, which means occupancy of all the nodes of the index tree has to be at least 2. Okay, so it's between 2 and 2 times 2, so that's your D. So now how does the search algorithm work? Given the search key K, say you have a selection query that asks for select star from movies where movie ID equal to, I don't know, 16. And now, instead of doing a full file scan to get the record with movie ID 16, if you have a B plus tree index on the movie ID, you can use this data structure to locate that record more efficiently. So now the search key K is given here, and then you compare the K against these index key values in the root node. Notice that all the key values that are stored in a page or in a node are stored in sorted order. So that's strictly not necessary. It does not change your I/O cost, which is what we're optimizing for here, but it does change your computation cost, your CPU cost. So these are two different things you need to worry about: I/O cost, CPU cost. In these sorts of scenarios, the I/O cost often ends up being the dominant, and that's what we worry about. But CPU cost is also important in some cases. If your list of index keys is stored in sorted order, what is the runtime for locating whether a search key is present or not, or where exactly does the search key fall? I can't hear. Log n, yes. If you have n entries in the page, you can do a binary search and you can get it in logarithmic time. So the computation cost is logarithmic in the number of entries. If the entries are not sorted, you have to do a full scan over all the entries in each page. Now that doesn't change the I/O cost. The I/O cost is still the same. The computation cost becomes linear in the number of entries. So for our purposes, we always have the entries of a page stored in sorted order. So now you have search key K comes in, you figure out which interval it falls in, take that pointer to the child, figure out which interval it falls in, and then take that pointer and you recurse until you hit a leaf node. Now once you compare with the entries in the leaf node, again you can do binary search or linear search and that will basically tell you that that key is present or that key is absent. Now, convention is these sorts of asterisks over here. You might be wondering why this one has asterisk and this one doesn't have an asterisk. It basically means it's a leaf entry. Okay, so it's a key value in a leaf page is denoted with an asterisk. So now here, if I say search for 7, how would this work? You come to the root, figure out that 7 means you have to go to the left of 13, come here, figure out that 7 is over here, and therefore it's a match. And then you take the record ID that is here and then return it to the query processing system. If the alt record alternative is used, the data record that contains the index key 7 is already present in the leaf page, and therefore you can directly use that. Okay? Does that make sense? Any questions? That's a very simple search process, right? What about 8? 8 is the key that you're looking for. So now come here, 13, go to the left, look here, largest is actually 7. 8 should occur between 7 and 13. There's nothing to the right of 7 in this page, and therefore you can declare that a search key 8 does not appear in the data set at all. It does not appear in the relation at all. Okay? Now you can note that there are these doubly linked pointers across leaf pages. We will come to why exactly that helps later, but for now just ignore that. For now, these doubly linked pointers are not very helpful for a search algorithm. All you need is the children pointers, figure out which interval you have to take, and then go to the children pointers. 24. Come here. Now you see that there is an index key that is 24. Which side do you take? This is a convention issue, and the convention is if you go left, you're strictly less than index key. If you go right, you're greater than or equal to the index key. There's no need that this convention should be followed. You could have the equality on the left as well. But for our purposes, we're going to enforce the convention that equality means you go to the right. Come here, 24 is a match, go to the right, come here, look at the lowest entry, binary search, 24 is a match. Therefore you return that record. Does that make sense? Now, range search, 19 to 33. You have a predicate that asks for returning all the movies that movie ID is greater than or equal to 19 and less than or equal to 33. How would a big plus tree be helpful here? Well, as I mentioned before, you start by doing an equality search for the lowermost value of the range, 19. So you come here, 19 falls in between here, take this pointer, do a binary search, 19 is right here. So that's your starting point for the records that match this predicate. And then you do a sequential scan. Everything that comes after, you just read it and make sure you apply the predicate that is less than or equal to 33. Keep looking at all these entries in this leaf. You've hit the end of the leaf. Now you take the pointer and go to the next leaf directly. You don't need to go back to the root. You don't need to search anything again. The entries in the leaf level are stored in increasing order of the index key. So you know for sure, as you scan linearly up the leaf level, you will hit 33 at some point, or you will reach the end of the file before reaching 33. So here 22, 24, 27, all of these are matches. So you keep returning these records. Then you take this leaf and come here, and now you see 33, it's a match. Then you see 34, and then you say it doesn't satisfy the predicate, you stop. Okay? Once you stop here, you know that nothing else to the right is going to match the predicate because the leaf level is stored in sorted order of the search key. Any questions? Pretty simple, right? Search process. So this is a generalization of your binary search tree. In your binary search tree, you only have 2 children. Ternary search tree, you have 3 children. Here, you could have any number of children that is defined by this parameter order. Okay? So what exactly does the page format look like? How do we pack these search keys and pointers into the page? We looked at record layouts, the page formats for packed, unpacked, and all of that stuff. What does an index page look like? Those things were for storing the relation as a file, heap file. Okay. How does the index file look in this case? So for a non-leaf page, the layout is different from a leaf page. For a non-leaf page, which is an internal node of the index tree, these are the things you lay out. You lay out P1, which is a pointer, K1, which is a search key value or index key value, P2, which is a pointer, and all the way to PM plus 1, which is a pointer. So by pointer here we mean a page ID, and the DBMS will know from the page ID where is the next child page. Okay? So that's it. So these are the values you store that you pack onto an index page. That's it. There's nothing else. There's no need to store a directory. There's no need to store offsets. As long as these index key values are of fixed length. Okay, for now, let's assume the index key values are from a fixed length domain, like an integer or a floating point. Okay? It becomes tricky if the index key is a variable length field, like a name or an address. You can actually build index trees on strings. Then the keys will become variable length. Then you have to worry about packing them in a variable length record format with delimiters and stuff like that. But now let's assume the index key is fixed length. It's a very simple slotting mechanism. You have pointers. Now you know which value to compare. You know the length of the pointers. You know the length of the key domain. Therefore, you can do an easy binary search within the page. And all of that is in memory. It's just computation cost. What happens? There's a change of notation here. So M is used for number of key values stored on a page. Earlier I introduced notation D for the order. M is equal to 2D. That's the maximum number of keys you can store on a page. And the order, which is D, is basically half of M. And what a B plus tree ensures is that apart from the root, every other index page has occupancy at least M over 2. Occupancy means all these pointers are valid. If any of these pointers is null, that means there is no child there. That means it's not occupied. Only the root node is allowed to have occupancy less than 50%. What does a leaf page look like? Now it depends on your alternative. If you use alt record, alt RID, alt RID, there are 3 alternatives. Now here, for example, we use the alt RID alternative. You still need key value. So that's your K1, K2, Kn. But you have the data entry, which is R1, R2, all the way till Rn. Okay, so these records, these entries depend on what alternative you follow. In this case, it's alt RID, so each entry here is a record ID that points to a record that lives elsewhere. This record could be living in a heap file that is separate from the index file. Okay, so then the DBMS will know, it comes to the leaf level, it knows, oh, I need this record ID, and then it will ask the file management subsystem for the heap file to figure out where exactly is that record. If you use the alt record alternative, this entry over here is the actual data record itself. There is no need to do any pointer chasing. You can just return that record directly to the query processor. Okay? There is no need for something else after this key. There's just this record associated with this key, but you could also pack something else after this key, but for convention, we just assume there's nothing over there. And then there's 2 pointers. Like I said, it's a doubly linked list. There's a pointer to the next leaf. There's a pointer to the previous leaf. Okay? So every leaf page has a pointer going to the left and a pointer going to the right. Obviously, the leftmost leaf, this pointer is null. The rightmost leaf, this pointer is null. Notice that the index pages, the non-leaf pages, do not have these pointers that point to your siblings. They only have pointers to the children. Any questions? Yes?
So the page size for non-leaf and leaf, are they going to be the same?
They are going to be the same. Yeah. The page size is the same, and it's fixed for the whole DBMS. It's the same page size as your heap file, any other index structure, and whatnot. Okay? Any other questions? Not rocket science, right? It's just simple data structure and file layout design. Okay. Now, what is a typical value of the order of a B plus tree? What is the number of keys you can pack? Now, it depends on the page size, of course, but typical page sizes, if you say 4 kilobytes or 8 kilobytes, you can pack, say, 100 keys, which means the order is, so M is like 200. So, like 4 kilobytes divided by 200 is like 8 some bytes. So, 20 bytes, something like that. So 20 bytes is like 8 for the key and then maybe 12 for the pointer. But you don't have to use up the entire page to store the key values. So typically in the real world, when people build B plus trees, the order is about 100. That means you're going to have up to 200 key values. That means you could have up to 201 children for each node. So now if you say the occupancy, which is the number of key values that actually exist on the page, is typically kept at 67%, that means even though you have spot for 200 index keys on an index page, you only store up to say 133. You deliberately make sure that the occupancy is not close to 100%. And when you do that, the actual number of children is called the fan-out factor, and that works out to 67% of 200, which is 133 roughly. So that's the fan-out, which tells you what is the exact number of children pointers that you have on each page. So now how do you compute the capacity of a tree? The capacity of a tree means how many records can it index. Clearly, the number of records you can index dictates the size of the tree. If you have only 10 records, you don't need a very big tree. If you have a billion records, you need a bigger tree. And so, if you have only a tree of height 1, that means you only have the root node and the leaf pages. And that means with the fan out of 133, which means every node has 133 children, you can only store 133 leaf pages, right? You have the root node, then you have the leaf pages. All the way to height 4, then it goes up exponentially. Now you can store 312 million leaf pages. And if each leaf page is 4 kilobytes, then that's like 1.2 billion kilobytes, which is 1.2 gigabytes? No, actually terabytes. That's the size of the leaf level of the index with a height 4. You can see it explodes very quickly. It's a very efficient data structure. You only need a height of 4 to index these many records. Okay? Any questions about this calculation? So the fan out is literally the number of children you have for a particular index page, and that is typically lower than the capacity of that page. And that lower means you want to maintain an occupancy of roughly 67% instead of having an occupancy of 100%. So what is the advantage of having a lower occupancy? Why not pack everything and have it completely packed and have 100% occupancy?
You have to keep creating new pages.
Sorry?
You have to keep creating new pages.
When? Inserts, yes. When you have insert operations on the B plus tree, if your pages are all completely packed, you would have to do a reorganization of the tree for the insert operation, which we will get to next. But if you have occupancy that's less than 100%, then you have space. And that means your records can sit in the same data structure on the same pages, and you just add an entry that's valid. Okay, so think about it just like the room capacity. If you have like 50 students in a room of 100, and now more students will come in, you still have scope 50 more students can sit here. But if your class is jam-packed, there's like all the seats are taken, now you can't accommodate more students. You have to overflow onto another room. So that's why occupancy is deliberately kept lower than 100% if you have inserts going on. Now if you have a read-only workload where you're sure there's not going to be any inserts, you can amp up the occupancy to 100% and your fan out will basically become 201. Okay, does that make sense? So the height calculation, how it affects the number of leaf pages, that is pretty simple, right? It's just exponential in the fan out. So now if you have a height of 3, the number of leaf pages is going to be 133 raised to the 3. Okay, does that make sense? And this is the calculation for the number of leaf pages. How many record entries or how many data entries are there on the leaf page is entirely dependent upon the alternative that you follow. If you follow Alt-RID, you can calculate very easily how many records pointers are there at the leaf level. If you follow Alt-Record, you need to know the schema. You need to know how big is the record in terms of bytes. Only then can you calculate how many records can be packed into these many pages. Yes?
So here, leaf page is the list. I mean the list or array on the leaf.
The what?
I mean the leaf page here.
Uh-huh.
So why is the 133?
Why is it 133?
Yeah.
So here the fan out is 133, right?
Yes.
So if the tree is of height 1.
I mean how to decide according to the page size or the, I don't know, other parameter of these.
So if
Memory
you're
or
given the
CPU.
fan out,
Yeah.
that is all you need to determine the number of leaf pages.
I mean, if we want design
If you want to design the B plus 3 index,
yeah,
how do you decide what the fan out should be, or
yeah.
what is the question?
So how, I mean the fan out the size.
Uh-huh.
So for the every non-leaf page, what's the size of the?
Right, so that is determined by the size of the index keys domain. So if your index key is fixed length, you can quickly calculate it based on the page size divided by the page pointer size plus the index key size. Right, so if it's an integer, then you know the size, it's 4 bytes.
Okay.
And the pointer is going to be 8 bytes. And so then you know 12 bytes is one entry for that, and then you can calculate how many
So it
pointers.
means one page is exactly the size of the page.
Yes, 4 kilobytes. Yeah. It's the same page as we were talking about before. Everything is stored in pages. Okay, so is this clear, the calculation? So if height 1 means you only have the root and then you have the leaves. That is it. Height 0 means you only have the root. Okay, so if it is height 0, you only have the root. If it is height 1, you have the root and then you have leaf. Because the fan out is 133, there are 133 valid pointers going out of the root, and therefore you have 133 leaf pages. Now if height is 2, you have the root, you have an intermediate level, and then you have the leaves. The intermediate level, each node still have 133 as the fan out, and therefore it becomes 133 times 133, which is 133 squared. Extrapolating height h, it's 133 raised to the h. Okay, so it's just exponential in the height. Any questions? Yes?
So this also implies like for at least like the non-leaf page, how many overhead, how much overhead you need for the B plus G.
Yes.
Yeah. So
The
say one lower order of 133.
The overhead?
Yeah, like for like kind of the non-leaf page.
Uh-huh.
So for example, if you had height equals 4, then the non-leaf page would be 133 over to the third layer.
The number of non-leaf pages.
Yeah.
So the number of non-leaf pages is going to be 1 for the root, plus 133 for the first level, plus 133 squared for the second level, plus 133 cubed for the third level. That's the number of non-leaf pages. If you add them all up, that is still quite a bit smaller than 133 to the 4, which is the number of leaf pages. So it's logarithmic, right? So it's an exponential. If you take the inverse, it's the logarithm. Okay? Any other questions? Yes?
But isn't that the page size fixed, the number of fanouts is
The page size is fixed, yes.
But like the number of fan out is actually fixed because we know the length of the key.
Right, so the fan out becomes a function of the page size.
Okay.
You need to know the page size to be able to determine the fan out.
Okay.
Like the fan out cannot go arbitrarily high because you may not have space on a page.